Hi everyone. In this lesson, we'll learn another classification method using probability-based approach, called as naive Bayes. Before discussing the classification method, it would be useful to start with the traditional term probability. Probability is a concept that measures the likelihood of an event occurring. In simple terms, the probability of a particular event can be expressed as the frequency of occurrence of that event out of all possible outcomes. Given enough repetition, probability values are represented by a value between 0 and 1. Here, a value of 0 indicates that the event will not occur, and a value of 1 indicates that the event will occur. If a dice is rolled, the probability of getting a 5 is 1/6. Because there are 6 different faces on the dice and each of them can produce equal probability. Another important concept for naive Bayes is conditional probability. Conditional probability measures how the probability of an event occurring changes if we know that another event has occurred. Mathematically, it is expressed as the probability of event A relative to event B and is denoted as P A B. Here, event B represents the event that we know has happened before, while event A is the event whose conditional probability we wonder about. Let's interpret this with a Venn diagram example. Imagine there is a database that records various characteristics of candidates for the basketball draft. In this database, let A represent the set of thin individuals and B represent the set of tall individuals. Suppose a coach looking for a thin candidate learns that the next candidate is tall. To satisfy his curiosity before the candidate arrives, the coach plays a little game. The coach first selects all records in the database belonging to set B, and then marks those among them that also belong to set A. Here, the coach calculates the probability of the incoming candidate being someone he wants by dividing the number of candidates in the intersection of sets A and B to the number of candidates in set B. Conditional probability forms the basis of both Bayes and naive Bayes methods. Let's look at Bayes' theorem first. Although it was discovered by Thomas Bayes, it was Richard Price who introduced it to the world 2 years after Bayes' death. In 1763, Bayes' theorem is based on a slight modification of the equation defined for conditional probability. This modification, denoted by the first arrow, utilizes the commutative property of the intersection operation in sets. The reorganization, denoted by the second arrow, proposed that an unknown conditional probability could be calculated using the other 3 known probabilities. Let's now look at an example where this theory is used in classification. Suppose the probability of any person in a city having cancer is 0.8%. And we have a test to detect cancer. It is known that the probability of having cancer is 0.98 for individuals who test positive. Plus, while the probability of being healthy is 0.97 for those who test negative. Minus. We immediately write the data from the question mathematically. After these values, shown with red circles, are written, we obtain other values by calculating their complement. Let's say someone whose test is positive comes to us and we are asked how to find out whether this person has cancer or is healthy. When we substitute these values into the equation we learned from Bayes' theorem, the probabilities of both cancer and being healthy can be calculated. When comparing the results, it is determined that the probability of not having cancer or being healthy is higher. Consequently, according to Bayes' theorem, it is suggested that the probability of the person being healthy is greater. This is indeed an interesting result. Despite having a highly accurate test for diagnosing both healthy and sick individuals, the test result indicating otherwise can be surprising. Imagine a doctor who tells you not to worry about the positive test result and continues. There are so few cancer patients in this world. How could you be the one to have it? Quote, "This inconsistency highlights the importance of understanding the interplay between test accuracy and disease prevalence, and the necessity of further investigation in medical diagnostics." At this point we need to mention another minor revision. Since Bayes' theorem is used here for classification, the denominators for all classes are the same and therefore can be ignored. This type of estimation is called maximum a posteriori. Looking at the values circled in green, it can be said that the test used for diagnosis is quite successful. However, the algorithm did not trust the success of the test and predicted the opposite class. Analyzing the situation, it becomes clear that we need to focus on the values circled in red. These values have diverged due to the imbalance in the number of healthy and sick examples in the dataset. If the number of classified data in the dataset is unbalanced, in other words, if there is a significant difference in the number of examples between classes, the results can be adversely affected. This situation is called class imbalance, and especially when one class has significantly more examples, probability-based algorithms tend to give more weight to that class. This makes it difficult to accurately predict rare classes. When there is a situation where it is difficult to rely on a single test and more input parameters need to be used together, as in the example, it is necessary to extend Bayes' theorem. At this point, we encounter the naive Bayes equation. In this equation, which seems very simple, the term maximum argument, meaning the one with the greater probability wins, is used. Now let's solve an example where we can apply naive Bayes. On the screen, you see a classification dataset with 10 examples. This dataset has 4 input features and 2 classes as the output. Let's find the class of a new sample that comes as less than yes, no, yes, yes greater than using the naive Bayes method on this dataset. When you quickly check whether the desired sample is in the dataset, you will see that none of the 10 lines contain a less than yes, no, yes, yes greater than line. So we can truly call this an unknown example. First, we calculate the probabilities and substitute them into the naive Bayes classifier equation. Then we compare the 2 probabilities we obtained. According to the maximum value, we determine that B is selected as the class of the yes-no yes-yes example. But we should not forget that we are only working with categorical data here. So, we have a problem to think about. If we had a feature that contained numerical data, how would we calculate the probability? Because it has been proven in many real-world problems that the independent variables have a normal distribution and is considered simple for mathematical convenience. Gaussian distribution is considered as a standard for many methods. We can use a similar approach to calculate the probability of numerical data. Although it is often associated with categorical data, it can also be effectively applied to numerical data by assuming a distribution. Most commonly the Gaussian normal distribution. When dealing with numerical features, the naive Bayes classifier assumes that the continuous values associated with each class are distributed according to a Gaussian normal distribution. In the Gaussian distribution whose probability density function is given below, mu and sigma values are the mean value and standard deviation of the numerical feature, respectively. Now let's solve an example with a zero-frequency problem. On the screen, you see a classification dataset with 10 examples. This dataset has 4 categorical and 1 numerical features as input and 2 classes as the output. Let's find the class of a new sample that comes as less than yes, yes, no, no, 45 greater than. In this question, we will not talk again about how categorical data is processed in the naive Bayes method. Focusing directly on numerical data, we will see how the Gaussian distribution is applied to the data. First, We calculate the mean and standard deviation of the rows belonging to class F. Then we repeat the same thing for class M. You can see these values marked in red. We can then calculate the probability values for x equals 45 by substituting these values into the function of the Gaussian distribution. For convenience, we have rounded one of them to 3% and the other to 5%. When we substitute all the values, we see that the result slightly favors class B. When we substitute all the values, we see that the result slightly favors class B. If yes was asked instead of no as the fourth property of the unknown sample, we would have a small problem. If we focus on the rows belonging to class F and the columns with property V4, you will get the table on the screen. I will pose the problem in the form of a question. How can the probability of V4 equals yes be calculated among the samples known to be class F in this table? In a naive Bayes classifier, if a feature value never appears for a given class, it results in a zero frequency problem. This zero value can make the entire probability calculation zero, negatively impacting classification performance. The most common method used to overcome this problem is Laplacian smoothing. Laplacian smoothing works by adding a small constant to each count value. We will generally use a number like 10 to the -2. The dataset on the screen contains 3 categorical and 1 numerical feature. Our question is based on the example K, P, T, 6. To include the zero frequency problem, the Laplacian smoothing factor is set to 10 to the power of -2. At this point, you can pause the video and try to solve the question. You can then continue to see the steps and the result. When we substitute all the values, we see that the result clearly favors class S. Thanks for watching. We recommend that you attend class for in-class activities.